So today this is the first lesson of the introduction to AI lesson. Okay, in the first place we need to give the problem formulation to understand the AI. Okay, first of all, suppose that we have this kind of equation: y is equals to the 2 times x. Okay, and x, for example, is the gas oil. I'm sorry. Gas oil price, and Q is the how many liters are taken, and also Y is the total price. So in this case we can easily calculate the whole prices that we need to pay it. Okay, and so in this case we can draw this kind of diagram. First of all, this is the x and this is the y. Okay, and also we can draw this line in terms of the what, the, for example, this is the 5 and this is the 10. Okay, and this creates to what a model that we can understand. This is simple, right? And so if you have any price in here, the gas oil price can be calculated by the x, and so we can multiply this x with the what, with the liters in here, and also we can calculate the y. This is a simple model in order to calculate how we can obtain the equation of the what of this process. But assume that we have square form of this equation, like this one. Y is equals to the what? A times x squared plus b times x plus c. Okay, and so maybe the calculated x and y can be drawn just like this one. This is the output, right? This is the input. In this graph is entirely dependent on the what, the a, b and c coefficients, and so we can generate the formula like this one, right? But normally we have this form of equation related to parameter. But what if we don't have model or ABC coefficients in here? First of all, we have the linear equation in here, and so this is the square form, and also we know the A, B and C. Okay, and then we can write that this output in here. Okay, but what if we don't have model or A, B, C coefficient? Okay, how we can build the equation or this formula or the output based on the what, the A, B, C? But this is unknown. Okay, and so in the general process, in the engineering perspective, we can write a solution just like this one. Ali, I will answer your question later. Okay? In order to solve this modeling, we propose some candidate function like this one. Y is equals to the what? Ax squared bx plus c. Okay? And so, which we don't know the a, b, c. Okay? This is unknown in this case. And so, we can take some points on graph, like for example, if we have any graph for a given data x and y, and so we can write that first of all the y is equals to the 0, and so a times 0 square plus b times 0 plus c. Okay, and also 1 is equals to what? For example, the a times 1 square plus b times 1 plus c. Okay, x1 and y1, and it goes on to the what? For example, the 100 a times 100 square plus b times 100 plus c. Okay, this can be solved with the what? With a linear matrix solution, guys. Okay, and so this can be applied to find out the values of a, b, and c in here. Okay, and so if we have this nomination in here, and so a, b, c is a vector in here, just like this one, and so we can create the matrix, and also we can create or generate the y in here, and so this is the r x result, xr. Okay, and so if we take the inversion of this xr values in here with multiplying with the y, gives us the a, b, and c. But this is the exact solution. This is exact solution with specific points. However, in real life or real implementation, we don't have such kind of information or the linearized or the ideal solution. We don't have an exact match. Only the approximation of these values. Okay, which means that we can approximate the solution, but we cannot find at every case to the solution. In some cases maybe, but we don't have the general rule to solve this equation in analytical form. Okay, and so in the new question we can write that the new question is arising from this one. These are the problem. How can we find a specific formulation of the data that are measured in real application? These are the question. Okay, So if we want to solve this question, then so we should give or propose the new method or the methodology to what? To approximate this solution, which means that we can utilize to the what? To the optimization technique. Based on this information, we cannot find the exact values of the A, B, C, even if we are using the linear theorem, because it's a non-linear. Or if we have the A, B, C, and so we can generate the output, but maybe this equation exactly is not the same with the real one. Maybe we have the x over 3 or x over 4 in this equation instead of using the square form. Okay? And so how we can prove it? In order to understand these terms, we need to turn into the least action in real life problems. Okay? We should utilize the optimization in here. But what's the proof of the optimization in the real life applications? In physics, we have an excellent notion about the nature in which nature always seeks or search the minimum energy form. Or states, which means that if we have any process or any system, this system is always seeks the minimum energy states in order to what? In order to make or do some process or the task, okay? Which we call it the least action in physics or in nature. Or the nature always find out the most efficient way from one point to the another. This could be energy, or this could be a position, or this could be a velocity, or this could be a energy, position, velocity, or something like that. We can convert this point into the what? Into the any physical phenomena. Okay? And so this is called in totally a least action. This is the rule of the nature. Okay? And nature is lazy, which means that it doesn't like to convert energy from potential to the kinetic one, or vice versa. If any energy form or the mass or the something like that is stayed at one point, and so it stays all the time. And so how we can solve this problem based on this formulation? Because in order to build our model based on the A, B, C or the some equation form, we need to utilize optimization. But we know that the least action is applied on the physics, on the real life application or in the nature. And so how we can prove it? How we can prove the least action is current or the exact representation of what the nature behaves. And so in order to do that, we need to give some problem formulations in here. Again, suppose that we have a certain time. We know the particle where it is. For example, if this particle in here, and so we need to go to the what? To the this one, okay? And so we have the optimal path in here. This is the least path or least energy path in here. Okay, but we can go to the what to this direction, or this one, or this one, or this one. Okay, and so this is the Q1, T1, and Q2, T2. Okay, but the best pathway is the what? Is the black one. Okay, and so it has a potential to be set in here. Okay, but the particle is moved by unknown effect. Maybe it's a torque or the force, we don't know, but and the position is changed like this one. Okay, and so if the nature always seeks the minimum energy states, and so in real life Q1 is moved into the what? Into the Q2 in the best pathway. But what is the proof, or where is the proof of these terms? In order to understand that, we need to define these formulations in here. We can define energy transfer formula like this one. The Lagrangian can be defined based on the what? The kinetic energy minus potential law. Okay, potential law. Okay, and so this is the Q and this is the Q hat. Okay, and so in order to move to what? To this particle into the Q2, we need to transform the kinetic energy into the potential one, or potential energy must be converted into the kinetic one. This is the Lagrangian, guys. Okay, it's the famous theorem in order to what? In order to solve the Earth's dynamic problem. But what is the relation between the building model in the artificial intelligence, or building the model equation or optimization? We will learn it, but how? If we have this problem, and so in order to find out what is the pathway in here, and so we can propose the solution just like this one. If the nature seeks minimum, we can write that action S. This action is called maybe force or torque or voltage or something like that. Okay, this is the applied energy to the system. But how we can formalize this form? So if we have this action, we can write that as Q are the R positions in here, and so as Q is equals to the what? T0 to T1, and L Q Q dot and T dt. Okay, and so we need to find out the minimum values of the SQ in here. This is the behavior of nature. We know it, okay, by the observations or something like that, right? And so in order to solve this problem in the mathematical formations, and then we can write that. Now assume that we propose the QT. This is the big Q, okay, and so it's the best pathway, okay, and minimize the what? The SQ. This is the energy formation, and so this is the best path. for the what? For the QT, guys. Okay? And so, if there is, this is the mathematical proof of this. If there is any increase or decrease, this path leads to the what? No minimum point or inefficient solution for our case, right? And so, in order to prove it, we need to write the QT is equals to the what? Big QT plus some small change in the past pathway. Okay? This is the small change in the path. And so, this is not a minimum. No minimum is given in here. Okay? And so, putting these equations in here with the what? With the change of these terms. And so, this SQ can be written just like this one. T0 to T1. Okay? And so, this Lagrangian is the total energy form in order to define to the what? The kinetic and potential energy transfer functions. And so, this Q is a path because the Q is given here plus delta, and Q hat or the dot plus delta dot, and T. dt can be written just like this one. But how we can analyze this one? This one is always greater than to the what? To this one. T0, T1, L, Q, Q dot, and T dt. This is the basic equation form to the what? To the best pathway solution. Otherwise, the nature does not seek to what? To minimum form. Okay? And so, how we can solve it? In order to solve it, we can utilize the Taylor expansion formula. Guys, see, in order to solve this equation in Taylor expansion, we can write this SQ just like this one. SQ T0 to T1, and so L Q Q dot T plus DL DQ delta plus DL DQ dot delta dot plus blah blah blah. Okay? dt. This is the main form or the Taylor expansion coefficient form in here. This is the constant one, but the other terms is the what? Is the expansion form of this one. Okay? And so, but we know that this is the minimum, right? And so, this term must be destroyed, right? Otherwise, we cannot say we are wrong, right? Because if this is the minimum point, and so in the Taylor expansion, the other terms must always be going to the what? To 0. Otherwise, we cannot reach to this minimum value. Just see, in this case, we propose the R equation, mean SQ. This is the what? The condition of the behavior of nature, seeking to what? The least action. And so after that, we define the QT in here as a pathway, best pathway, right? And so after that, in order to break this condition, we add the QT with what? Big Q plus small change in the path. And so we can write it. And after that, we can propose or we can use the Taylor expansion in order to what? In order to get the dynamics of these equations in here. And also we know that this is the minimum point. But the other terms must going to the what? Going to the 0. Otherwise we are wrong. And so, how can we evaluate these conditions? In order to solve this problem, we need to utilize the calculus of the variations. Okay? the main problem right now is the how we can evaluate these terms. Firstly, we need to give this condition. We need to keep delta term since its position we have, right? After that, we need to define dl dq times delta in terms of delta, because it's the change in pathway. But this is not, and so we need to remove this term in order to solve this problem, because we need to minimize the positions values of these terms. And so in order to solve this problem, we can write it this way: d over dt dl dq dot times delta must be equal to what? D dt dl dq dot times delta plus dl dq delta. And so this is coming from what? The calculus of the variation. This is the partial integral form of this equation. Okay? And so if this is the true, and then we can write it dl dq times delta dot must be equals to what? D dt dl dq dot times delta minus d dt dl dq dot times delta, right? This is the R form, and so we have this term, we have this term. We need to put this equation into what? Into the left hand side. Okay? And so just see that we define all the term in terms of the what? The delta terms in here, guys. Okay? And so in the last case, we can write the R as Q functions in here. SQ is equals to what? S greater Q, because it's coming from this minimum value, right? Because in the this is the what? The summation form of these terms, and so we can separate this integral from to this one. And after that, we need to use this equation into the what? Into the Taylor expansion form in here. And so plus integral form t0 and t1 and t1 dl dq times delta minus d over dt dl dq dot times sigma or delta, which is coming from these equations, and plus d dt dl divided by dq dot times sigma plus blah 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 and over dt can be written just like this one. Okay? So how can we utilize these terms in here? First of all, this is going to the what? Going to the endpoint value. Okay? Because if we have the endpoint, and so this sigma value must be what? Must be going to the what? The sigma 0, right? Because there's no change in the what? In the pathway. And so this integral is turned into the what? We have the maximum values in here, but also we have the delta s in here, t0, t1. And also we have the integral form in here, dl partial derivative of the dq minus d dt dl dq dot times delta plus blah 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 and dt. Okay, these are the general form of this one, but we should know that this value cannot be 0 until at the endpoint. We remove the endpoint calculation because we cannot change in time at the endpoint of these terms, and so this is removed, but the other terms cannot be removed in here. And so in order to prove our theorem, this must be going to the what or equals to the what equals to the 0. And so if this term is equals to the 0, we can write that d over dt dl dq dot times dl divided by dq must be equals to the 0. And so this is called the Euler-Lagrange equation. And so it's coming from the what? The optimization solution of least action theorem in nature. And so if we have this form, and so we can create some dynamics based on the what? Based on the R system. But this is coming from the what? This is coming from to the solution of the best pathway solution to the what? To the Lagrangian form or the energy form of these terms. And so if we have this formulation, and so we can write easily just like this one, dl dq dot minus dl dq may be equals to torque or force. This is the what? The general form of the system dynamic equation, especially for the robot dynamics or the nonlinear dynamics. We can utilize these equations if we have the kinetic and the the potential energy one, and so we can use this formulation to to our equations. Okay, and so we can write these conclusions in here. This is important. The dynamics related to universe are directly derived from the minimization principle, guys. Okay, its feature and effective part are described using this notion. Okay, now data set. Like, for example, if we have the x and y, x is input, y is output, and also we have this kind of data, x corresponding with what? With y. Okay, and so the problem is how can we model, evaluate, and find the proper notation or notation of in this form. Now we know that we can use the minimization principle, right? Because we know that in the universe, even if the universe have the minimization principle, and so why we can't use this rule into the R dataset? We can use it, right? And so how we can model it? And so we can summarize the whole process. If the data are available, then we can say that there is a model, right? Or dynamics, right? But in this dynamic, this is not the time dependent, this is the x dependent, right? So y is a function of the x, not the time. But we can write it because we can use the math at every variable. If there is a dynamic, so it should be resulted of some minimization problem, right? Otherwise we cannot use it, because in the nature, even if the nature has this property for the dynamic system, and so if this is the data set coming from the universe or the some process, and so it must be obey to the minimization problem or the minimization rule, right? And so in the third case, if minimization problem can be constructed, so then we can find the model, or even learn from any data, right? We can find the model or even learn the data. Otherwise we cannot drive the Euler-Lagrange equation. Euler-Lagrange equation is an exact solution for the for the dynamic behavior of the physics in the real life. But if we have the data set coming from the nature or collected from the nature, for example some sensors or the actuator or something like that, and so we should apply the same rule just like the minimization problems, and so we need to build the model. Otherwise it's not coming from this universe. Okay, so as a result we need to collect the whole terms in here. Every dynamic or action, this is the general name of the dynamic. Dynamic is called to what, or dependent of the time, but the action is a universal name for this. Determines the measured data from the nature, right? If this is wrong, and so not live in here, and so this data is coming from the or stored in the universe. And so in order to create the dynamic formulation, the minimum principle must be utilized, right? And after that, if there is no information about the model, and so we can use minimization of energy that we define, right? Otherwise we cannot apply the Euler-Lagrange equation into the dynamic system, right? And so in the fourth place, in universe, the kinetic and the potential energy are stored. Either we cannot destroy or create this kind of energy, but we know that all the time the kinetic is transferred into the potential one, or the other case is correct, right? But in changing all the time, right? So therefore if we have any data in mathematics, and so we can define energy function and minimize it to find out correct model. Okay, and so in the last place, if every form is in the math notation, then we can learn it from data using this energy function. Otherwise we cannot model to this kind of information. Okay, and so in the first place we need to summarize the whole process. We must utilize the measured data from the nature in the first place. In the second place, in order to create a dynamic formulation, minimum principle must be utilized, or this dynamic formulation must be obeyed with the rules of the minimum principle. Otherwise our physics is wrong, right? And so there is no information about the model. We can use the minimization of the energy, because the Euler-Lagrange gives us two ways to drive the dynamic system, even if it's dependent of the time, right? And so in the universe we always change the kinetic or potential energy, but we can define another energy forms in here. For example, the minimize of the cost in pricing to the oil. We can define it. There is no restriction for it. But in the universe we have the kinetic and potential one. But we can also define a cost function to minimize your budget, right? And so therefore if we have any data in the math, we can define the energy function just like the gas oil cost function, and we minimize it to find out the correct model. And so every form in the math notation we can learn from this data, because unknown pattern modeled by mathematical formation of standard function can be called as a what? Learning. Guys, learning. If we model the what unknown patterns by the mathematical formation of the standard function, this is called the learning. Okay? So, to learn from experience, recognize the pattern, understand natural language, and make a decision. Okay? And so finally, this is just kind of the simulating cognitive function of human. These three list or the conditions are the standard definition of the artificial intelligence, guys. Okay? Any question?